So today I'd like to finish up our discussion of the reactions of carboxylic acids. And I think this is going to be a nice chance for us to think about some more mechanism and really get to understand the reactivity of the carboxyl group. I think this will also be a chance to see useful chemistry. Point that I made earlier on, and I think your textbook does a nice job of this, is that all of the members of the carboxylic acid family can be interconverted. In other words, we talked about carboxylic acids, esters, amides, acid chlorides, acid anhydrides, nitriles. And I'm going to give you a smattering of some of that chemistry today, focusing on carboxylic acids and esters, and maybe to a little bit of amides, which we also tied in with nitriles in our discussion. So by way of sort of drawing what we're talking about, sort of written generically, would be compounds of this sort. Generically for amides, we've written this as NR2 prime. Of course, that also includes primary amides with an NH2 group, secondary amides, and tertiary amides. If I had to give one generalization, I know I said this before, I'd say that esters are less reactive toward nucleophiles than, say, acid chlorides and acid anhydrides. And by that, I mean that typically we are using acid chlorides and acid anhydrides as reactive species, although there are obviously compounds you can put in a bottle of. Your textbook has a nice picture of acetyl chloride fuming because it hydrolyzes in moist air. Acetic anhydride you can buy by the bucketful. It's used to make various types of fabrics like acetate, cellulose acetate, if you've ever worn any synthetic clothing that are made with acetate fibers. And yet, usually they are not endpoints in themselves, but species, not intermediates, which I've distinguished as things often you can't put in a bottle, but you have for at least a finite amount of time. There's species that you can put in a bottle, but they are reactive. Esters, on the other hand, are everyday compounds. They're your PETE water bottles. They are your polyester clothing. They are the fats in your body, grease on your skin if your skin is oily. They're also the cooking oil that you use for frying French fries or sauteing food. So they're common compounds, relatively stable, not super reactive. Amides are even less reactive. I'll say even less reactive. And I kind of made a point of that where I said all proteins are amides, nylon is amides, the proteins in your eye lens sit there for your entire life without breaking down, without hydrolyzing, although you may get cataracts from photoreaction, which is why it's a good idea to wear sunglasses. So in terms of carboxylic acids, I generally think of OH and OR as being very similar. In other words, whether we have an OR group here or an OH group, you get a similar degree of donation into the carbonyl group. And a lot of that determines the reactivity of these compounds. Oxygen has a certain electronegativity. I think it's 3.4 on the Pauling scale. And the R groups will make a small difference, but not a huge difference. But so in a way, I would say acids are like amides, like esters. But then there's a big but. They can react with basic nucleophiles as an acid. And when we were talking about organometallic reagents like methyllithium, I said methyllithium will add 2 equivalents to a carboxylic acid, to an ester. But by way of contrast, because methyllithium is highly basic, it will get protonated by a carboxylic acid. So for your purposes, you can say methyllithium doesn't add to the carboxyl group of a carboxylic acid. Under certain conditions, you can actually sort of force that reaction after the deprotonation. But at least for your thoughts, it would be carboxylic acids would quench methyllithium, would protonate methyllithium and generate methane, whereas 2 methyllithium groups would say add to ethyl acetate to give you tert-butyl alcohol. So those are the big differences. And then amides, the nitrogen is less electronegative than oxygen. It's better at donating in, so it even more satisfies the electrophilicity of the carboxyl group, and therefore makes them even less electrophilic, makes amides even less electrophilic by esters. So by way of calibration, if I take methyl acetate, just a simple ester here, but you could easily take a more complicated ester, and I treat it with ammonia, aqueous ammonia would be fine, anhydrous ammonia and an organic solvent would be reasonably good as well. If I take an ester with ammonia, that ester will react with ammonia. The ester bond will be cleaved to give you methanol and the acetamide. And that gives you kind of a feeling of the reactivity of the species involved. In other words, in a calibration scale, acetyl chloride would react like a shot. Ammonia is basic enough, is nucleophilic to do that. Ditto for acetamide. Methyl acetate would react a little more slowly, and acetamide wouldn't, well, be a degenerate reaction, but it wouldn't react at all. We call this reaction ammonolysis, literally cleavage, lysis, cleavage of the ester bond by ammonia. And the reaction goes by way, I'm not going to write out a detailed mechanism, but the first step of the mechanism, ammonia is nucleophilic, right? We use pKa of the conjugate acid as a surrogate for thinking about nucleophilicity. The pKa of ammonia, of the ammonium ion, is about 10, which means it's sort of moderately basic, right? By way of comparison, methyl lithium, the pK of methane is 50. It's super basic. The pK, if we're thinking about water as a nucleophile, we have to think the pKa of the hydronium ion, it's -1.7, so it's much less basic and much less nucleophilic. It gets a little tricky as you're comparing across different atoms like nitrogen or oxygen. But again, we're talking 12 orders of magnitude difference in basicity between ammonia and water. So that's a feeling. All right. I don't want to write out, at least not here, a detailed mechanism for the reaction, but I'll sort of write the first intermediate that you could think about. And the first intermediate that you could think about would be that ammonia attacks the carbonyl group to give a tetrahedral intermediate. And then some protons can shuttle around and the tetrahedral intermediate can break down to acetamide. You could probably write this reaction by a couple of what I would call reasonable reaction mechanisms. I tend to think of it as breaking down at this point, but you could also think of loss of the proton on the nitrogen and then kicking out methoxide anion. Anyway, as I said, we call this reaction ammonolysis because it's ammonia. If you want to get really subtle and fancy, we call it aminolysis if we're doing the reaction with an amine, primary amine or a secondary amine. I'll just write that as RNH2 or R prime NH2, and there you would get an amide. So what I was saying before about carboxylic acids, and I know I've made this point at a couple of times, is that if you go ahead and mix a carboxylic acid with ammonia, you get an acid-base reaction. And this is a reaction that you've seen since freshman chemistry. Ammonium acetate is the salt that comes when an acid reacts with a base, when acetic acid reacts with a base. So I'll say salt formation. Now, I think one of the things that your textbook says that's a little bit confusing is if you heat ammonium acetate, if you mix ammonia and acetic acid and kind of heat the heck out of the salt, you will get some acetamide. I never emphasize this reaction. I would urge you to sort of forget it. And the reason I say this is it's not an efficient way to make amides. It's not a general way to make amides. And while I wouldn't say it is wrong per se, I would say that I think that many beginning students get in the mindset that you can mix an amine or mix ammonia and a carboxylic acid and get an amide. And that's really not a good mindset to be in. We're going to show you by the end of today's lecture some good ways of making amides, some good ways of synthesizing amides. We're going to learn about the coupling agent DCC and various other diamides, particularly diisopropyl carbodiamide. And we'll also learn about making how it's very good. Remember, I said acid chlorides are often made on the way to something else. It's very good to convert a carboxylic acid to an acid chloride with thionyl chloride, or in some cases, other reagents like oxalyl chloride, and then go ahead and let the acid chloride react with the amine. All right, so again, by way of comparison and sort of self-calibration, if you have an amide, and I've just drawn dimethyl acetamide, and you treat it with ammonia, they're not going to react. So I'd say no reaction. So that's really the big difference between esters and amides. Esters are reactive enough to react with amines, albeit not super fast. Ammonia is relatively small and can be at high concentration. Other amines would react more slowly. But on the other hand, acetamide is just dead. It's just non-reactive, or NN-dimethylacetamide is just dead. It's just non-reactive to an amine. You know, put simply, what this means is you could go ahead and take ammonia, take household cleaning ammonia, and wipe your backpack with it, but you might not want to wipe your eyeglasses with it that are made, if they're made of acrylate plastic, because acrylate plastic has ester linkages. You would damage the plastic. And ultimately, if you used Windex with ammonia on your eyeglasses, you'd find that you perhaps cracked the lens from damaging the polymer. So that would be a little bit of an idea. All right, again, by way of calibration, and I was sort of hinting at this or saying this before, for all intents and purposes, water doesn't react with esters. So if I take methyl acetate and mix it with water, no reaction occurs, is the easiest way to think about it. And by that, I mean on the order of minutes or hours or even a few days. If I dissolved ethyl acetate in water and left the solution for a year, I might come back and there might be some acetic acid and some ethanol in there, even though the ethyl acetate wouldn't have thoroughly hydrolyzed. So it's always a question of relatives. I think another, I'd say, sort of maybe beginning misconception that students make is on ester formation. If I take a carboxylic acid and I take an alcohol like methanol and I mix them together, much by the same idea, we're not going to have ester formation. So I'd say no reaction, no ester formation. And I think that's important because we're going to see in just a moment how to make this reaction occur. But, you know, as I was looking over the exam, I think what I saw in many of the transformations was there was sort of a lack of understanding of how reagents and reactants work together to make a reaction occur. So for example, in a Friedel-Crafts acylation reaction, if you just mix acetyl chloride and benzene without a Lewis acid, they're just going to sit and stare at each other. But if you add aluminum trichloride, that's going to act as a reagent, or depending on whether you're doing a Friedel-Crafts acylation or alkylation, the exact conditions, it can be a catalyst. And so the difference that occurs really is the difference between having that reagent to activate to make an electrophile, in this case, more electrophilic, to make an acetyl chloride, an acyl chloride into an acylium ion. We're going to see that same thing when we look at the reaction of carboxylic acids and amines with or without DCC. So, okay, what changes the game in the reaction of carboxylic acids is the addition of a catalyst, is the addition of a strong acid like sulfuric acid. So if I take acetic acid and mix it with methanol and add some sulfuric acid, and it doesn't have to be too much, it doesn't even have to be a full equivalent because it is largely catalytic, then we get methyl acetate. And as a byproduct of reaction, organic chemists are terrible about writing reactions with their byproducts. You get water, so I'll put that over here. In a preparative sense, you'll often see a reaction as reagent to product. So if, for example, we have I'll just draw a different acid here. Does anyone know what this acid is called? This is called salicylic acid. Does that name sound at all familiar? It's in acne medication as a skin wash. It's a mild astringent. Anyone else know where else you might find compounds containing salicylic acid? Some of you might have even used it this morning. Yeah. To make aspirin. Acetyl salicylic acid is the acetyl ester. Typically made by treating salicylic acid with acetic anhydride. So you can make the ester of the OH group, of the phenol group, by treating salicylic acid with acetic anhydride. Salicylic acid is also present in addition to aspirin and aspir cream that you can rub on your muscles. It's also present with bismuth and Pepto-Bismol. Pepto-Bismol is bismuth subsalicylate. People have been taking this for years for your stomach. Only recently did they figure out the exact structure of bismuth salicylate. But where I was going was a little bit more of a fun reaction. And I wanted to get to writing reactions the way many an organic chemist would. If I took salicylic acid and I treated it, and often you would see this maybe written as even just use of a little bit of sulfuric acid in methanol as the solvent, you might see this reaction written this way. You would get this compound. Based on our discussion of nomenclature, what would we call this compound? What would be the name that we would call this? How do we name an ester? If the ethyl ester of acetic acid is ethyl acetate, what's the methyl ester of salicylic acid? What would its first name be? Methyl salicylate. Where have you heard of that? It's oil of wintergreen. It's the flavor in your wintergreen lifesavers, which taste really good, present in various medicines that you rub on your skin, like Bengay for sore muscles, another source of salicylic acid. It's got this incredible wintergreen flavor. It's a fun experiment to do. You take a test tube, throw in some methanol, throw in a little bit of salicylic acid, add a few drops of sulfuric acid, heat it up and boil it, and you can smell the wintergreen smell. So all of these reactions that I've written with acid catalysis, whether making sulfuric acid with methanol and acetic, whether making methyl acetate with methanol and acetic acid, or making methyl salicylate with salicylic acid and methanol, all of these reactions fall in the category of what's called a Fissure esterification. Named after the reaction's discoverer. I'd like to take a moment to talk about the mechanism of the Fissure esterification reaction. And again, I think that it really becomes very, very important to have the skills, not to memorize a reaction, but to think your way through, to understand the broad principles, and to figure out how the reaction occurs. So I've pointed out that the carboxyl group is not that electrophilic, whether in an ester or whether in a carboxylic acid. The carboxyl group is not electrophilic enough for a weakly basic nucleophile, a very weakly basic nucleophile like methanol or water, to attack it. But acid can protonate the carboxyl group, and that makes it much more electrophilic. So when you dissolve sulfuric acid in water, I've emphasized you no longer have sulfuric acid present. The sulfuric acid is way stronger than the hydronium ion. So you get H3O plus and HSO4 minus. And methanol is very similar to water. When you dissolve sulfuric acid in methanol, you no longer have H2SO4, you protonate the methanol, and that's the strongest acid that can exist. So I'm going to write that as the driving species in this catalytic reaction. So the sulfuric acid protonates the methanol. The protonated methanol now serves as a proton source. We can protonate the carboxyl group. I draw my curved arrow like so. I try to be a good person, keep track of all of my lone pairs and charges. Now, at this point, your carboxyl group is much more electrophilic because it has been protonated. And now even a weak nucleophile like methanol can attack it. And so you're doing this reaction in methanol. You've got a ton of methanol floating around. You've got many molar concentrations of methanol floating around. And that methanol now can attack the protonated carbonyl group. Electrons flow from the methanol to the carbonyl group. Electrons flow up onto the oxygen atom. Like so. We end up with a protonated tetrahedral intermediate. I'm deliberately writing things out very methodically here because this is the level of thinking or the level of ability that I would expect you to be able to have in thinking about a reaction like an ester formation. And once you master this level of thinking, and I hope all of you here really are already at this level of thinking, but if not, that's okay, because that's why we practice and think and get better. Once you master this level of thinking, you can go ahead and think your way through an acid-promoted ester hydrolysis, a trans-esterification reaction, and all of these end up being basically the same mechanism with the broad principle that protonation of the carbonyl group activates the group toward addition of a weak nucleophile. So in strong acid, protons come on, protons go off. You've got lots of methanol floating around. And you notice for this sequence of 3 steps that I've written here, we have sort of a degree of symmetry to it insofar as in the first step, we're protonating the carboxyl group. In the last step, and consuming a methanol, protonated methanol. In the last step, we're regenerating that. And so you see how the acid is catalyzing. Now, this hasn't taken us all the way to the ester formation. This has taken us halfway there. We have a tetrahedral intermediate at this point. And that's not a compound you can put in a bottle. It's not a stable species. It exists, but only for milliseconds or microseconds, and then it breaks down. And the breakdown is identical to the formation, except now we're going to, instead of adding methanol, we're going to lose water. So instead of adding methanol to the carboxyl group to form the tetrahedral intermediate, we're going to lose water. And the process occurs in the exact same pathway that we see as those 3 steps above, but in reverse. That's sometimes called the principle of microscopic reversibility. And I always put it as, if taking the 5 up to San Francisco is the fastest way or the shortest way or the easiest way to get there, then taking the 5 back down from San Francisco is going to be the same, is going to be the fastest way back or the shortest or the easiest way back. So, okay, we're going to break down our tetrahedral intermediate. I'm just writing the OH on whichever side is convenient for my drawing the mechanism. There's no particular difference. But that means since in the last step we removed a proton, here we're going to put on a proton. Protons go on, protons go off every oxygen atom. I'm taking us on the pathway that leads to the product here. All right, in the next step, our tetrahedral intermediate is going to break down. OH minus is not a good leaving group, but it needs something to give it a push to leave. So in a base catalyzed, base promoted hydrolysis, hydroxide or an oxyanion would push it out. But here we have enough push because we're kicking out water. In other words, we already have a positive charge. Oops, as I said, I've been trying to be super methodical and write things out step by step. So I'm going to do that for you here. All right, so here's our protonated species. You can kick out water. Now we're practically home. We have protonated acetic acid. And in the final step now, we can think of methanol coming along and removing that proton. So I can go ahead, and you'll notice again that in this set of 3 steps, we've started with protonated methanol, and we're about to end up with protonated methanol. So again, you can think of the methanol as being, the protonated methanol as being the catalyst in this reaction. Thoughts or questions here? Oops. I have, oops. Okay. I just went ahead and dropped my methyl group over here. That's what I get for chatting and not paying attention to what I'm doing. All right. So anyway, as I said, we kick out water, we end up with the methyl ester. What thoughts and questions do you have at this point? Yes. A great question. I love it. I really love that question. And you'll see me maybe differ from the textbook or some of the textbooks on this. I think what you're writing is, shall we say, reasonable, but not reasonable enough. So what you're saying, I already said in the beginning, you have HSO4 minus. This is a great question. This is really, really cutting right to the crux of basicity. And you say, okay, is it reasonable? And it sure as heck looks reasonable. And I'd say it's not bad, but here's why I would say it's not the best way to think about it. I guess in this case, we have the methyl ester here. All right, great question. I'm so glad you asked that. Okay, so you'll look at this, and the first thing you think is, hey, O minus looks pretty good. And yet, sulfuric acid is actually a stronger acid than CH3OH+. CH3OH2+. In other words, the methanol CH3OH is actually more basic than HSO4 minus. And that really spins with your head. In other words, even if this occurred, it would, even if we did have that deprotonation, this sulfuric acid would immediately react with the methanol to form CH3OH2 plus. But more importantly, CH3OH is actually more basic than HSO4 minus because sulfuric acid is such a strong acid, pKa about -7 versus about -2 or -3. Does that help? It's a real mind spinner. And I guarantee probably half the people here were thinking that or will think it when they wonder about this, when they look over their notes. So thank you so much for asking this. Other questions? Oh, thank you, HSO4 minus. Yes, thank you, Matt. Other questions, other thoughts? Yeah. In the very first step, the oxygen on the carbonyl. So pardon? It is. Okay, so you're asking a great question. So the pKa, and I will refer you to Appendix C for the exact numbers. The pKa for protonated methanol is about -2, somewhere around there. The pKa for protonated acetic acid is even a little bit lower, more negative, probably -3, somewhere around there. So this equilibrium actually lies a little bit to the left, about an order of magnitude. That's a goodly amount, but not that much. Protons come off, protons go on, protons come off. That oxygen may spend only a small fraction of its time protonated, but it's enough to activate it. So absolutely. And I think this is one of the first things you have to, that is hard when absorbing this chemistry, is sort of having that fluidity of mind to recognize how the chemistry goes and the fact that there are many different pathways. The other thing that's interesting, if you're looking here, is to say, okay, well, why did I go ahead and protonate this OH group rather than protonate, well, the two OH groups are equivalent. So, right, it's tetrahedral, they're the same. So that's not a big deal. But why didn't I protonate this methanol? And protons go on, protons go off. That's the reverse step here. So indeed, that will protonate. You will go back, you will go forward. But what's driving this reaction is the fact that we've got this huge excess of methanol. So this is being driven by the fact that we're running this reaction in methanol with no water present. If we ran the reaction in water with no methanol present, we'd have the exact process in reverse. In other words, if I then, having gone to the trouble of preparing methyl acetate, if I treated it with excess water and a little bit of sulfuric acid, it would happily, the ester would happily hydrolyze back to acetic acid and methanol. So the driving force is just what's present in excess. And since I've emphasized fluidity in how you write your chemistry, I'm also going to emphasize that you could write this reaction as H2SO4 in H2O. These would both be completely good ways of writing this chemistry. But in this case, we would just call this, instead of Fissure Esterification, we would just call this acid catalyzed ester hydrolysis. And I'm going to give you as sort of a thing to take home to write the mechanism. But you could go ahead and cheat. You just go ahead and just write the exact same mechanism that I wrote in reverse with hydronium ion and water, because we don't have a lot of methanol. In other words, in the first step, hydronium ion protonates the carbonyl of the methyl ester. In the second step, water attacks to form a protonated tetrahedral intermediate. In the third step, you take a proton off to get this tetrahedral intermediate uncharged. In the fourth step, you protonate the methoxy group, and in the fifth step, the OH pushes its electrons down and kicks out methanol. And in the sixth step, water comes and takes the proton off the protonated carboxylic acid, and you've hydrolyzed your methyl ester. But go ahead and try this on your own. It's a good exercise to try, and it's exactly the sort of mechanism that I'd expect you to be competent at, to be good at. Other thoughts or questions? Yeah. Great question. And this is where sometimes subtlety comes in. That's a fantastic question. Would we need to protect the alcohol? Not in this case. You have this huge excess of methanol. And so the methanol is not going to do anything with the OH group. So no, you wouldn't need to protect it. But it's an eminently reasonable question for you to be wondering about. Now, it's interesting. Aspirin has been a drug for well over a century. I have a bottle of acetyl salicylic acid in my office that's about 120 years old, from the Merck company, and it's been known and used for medicine for a very long time. And it's always interesting when people come up with a new twist on it, because remember, acetyl salicylic acid, I said, breaks down to salicylic acid. That's the active form of the drug in your body. Acetyl salicylic acid is called a prodrug. One scientist at Rutgers got the question, what would happen if I made a polymer of salicylic acid? Would it have properties as a medicine? And it does. And she did. And by making this polymer, your textbook goes ahead and gives so I'll just write this as basically sort of the et cetera. In other words, this continues to another salicylic acid molecule. This continues to another carbonyl. And the answer is yes, this has beneficial properties like aspirin. So you can go ahead under the right conditions and form ester linkages to the phenol group, which is sort of cool. Other questions? Aspirin does expire. It can hydrolyze adventitiously. If you smell a bottle of aspirin that's getting old, it has an acetic acid smell to it. But the bottle I have in my office has been sealed with wax, so no moisture can get in, whereas moisture gets into your aspirin tablets. All right, so on that note, let's talk about breaking down. Let's stop talking about aspirin. Let's talk about breaking down esters. the hydrolysis of esters by base. And whereas the hydrolysis by acid is catalyzed, the hydrolysis by base is stoichiometric, and you'll see why in a moment. If we take a strong base like sodium hydroxide or potassium hydroxide in water and take our ester with it, we get the carboxylate salt plus an alcohol. So in other words, it would be the sodium salt over here. And this process is called saponification. If you don't like a fancy word, call it base-promoted hydrolysis. But this is one of the oldest reactions in the world. People have been doing this for centuries before the field of organic chemistry was created. And it's a very, my iPad isn't cooperating here, but it's a very useful reaction. In fact, I would argue this reaction is one of the greatest advances for human health. So if we take this molecule is a triester of the alcohol, the trialcohol glycerin. It's a triglyceride, in other words, a fat. Same thing if you have a blood workup, your doctor might check for in your blood, triglycerides. If you take sodium hydroxide and water, in some cases this has been done with potassium carbonate, potash, and you cook up your ester, your fat, you get the sodium salt of the carboxylic acid. This carboxylic acid shown here is C17H35COOH is called stearic acid. It's from beef fat, like steers. And this is soap. This is what's in my ivory soap that I showered with this morning. The other byproduct of reaction is glycerin or glycerol. And I'd argue that this is the greatest advance for human health because it is the most basic form of hygiene. Before the 18th century, doctors didn't believe in washing, or into the 18th century, doctors didn't believe in washing their hands for surgery or for delivering babies or anything of that sort. And the result was all sorts of infections. So I'd argue this is one of the greatest things for human health. Thank you. Again, the risks of yammering and talking, yammering and writing. Questions about this reaction or about what we're talking about here? One of the things I've been emphasizing is the degree of relative nucleophilicity, often with a surrogate basicity. And so, whereas the carboxyl group in an ester is not electrophilic enough to be attacked by water, hydroxide is much more basic and much more nucleophilic. As OH minus, it has enough oomph to go ahead and add. And I'm not going to write out the mechanism in as much detail. I'd expect you to be able to do this because it really is all the same principles that we've been talking about, but I'm going to go ahead and perhaps write this a little bit more perfunctorily. And so your tetrahedral intermediate now under these basic conditions, that O- has enough oomph to kick out OR- to kick out your alkoxide anion. And that can pull off a proton from your carboxylic acid. And so one of the things you see in this mechanism is this last step is really irreversible. In other words, this final step, now we take a carboxylic acid, pKa about 4 or 5, and we take an alkoxide anion, and we get an acid-base reaction that for all purposes, although it is sort of an equilibrium, the alkoxide anion, the pK of the conjugate alcohol is 16 to 18. In other words, that final deprotonation lies so far to the right, more than 10 orders of magnitude, that it is for all intents and purposes irreversible. And so this reaction's driven by the formation of carboxylate. And if you write a balanced equation, you'll also see that it's not catalytic, that we started with a mole of sodium of hydroxide anion. We've ended up with a molar equivalent of alkoxide. And so that's a big difference here. Your textbook talks about liquid-liquid extraction, and to a large part, I've sort of relegated this to things that you do in the laboratory and things that you learn about in the laboratory. But I'll just point out that if you wanted to isolate the carboxylic acid, you could then add acid in a separate step. In other words, you would have completed your hydrolysis reaction. Your fat would now have dissolved in a solution of soap. You could add acid and HCl or H2SO4, and you would have your carboxylic acid, which you could isolate by liquid-liquid extraction. With your inorganic salts, like sodium chloride, staying in the aqueous layer, and your carboxylic acid moving into the organic layer. Thoughts or questions? Yeah. No, ester formation cannot. That's a great question. I love that you're engaging with the material. So let's imagine for a moment, we go ahead and we say, all right, let's imagine that I have methanol and acetic acid, and I mix it together with sodium hydroxide. As I said, that hydroxide is way more basic than the carboxylate. And so what's going to happen is we're going to get sodium acetate and the methanol is just going to sit there. They ain't going anywhere together. So in order for an ester to form, you need an acid catalyst or, acetic anhydride or acetyl chloride or something to that effect. Other thoughts or questions? Great question. All right, I'm going to leave the next one's examples to you, but I want you to think about this on your own. Students often in encountering cyclic compounds, particularly when you're beginning, find it somewhat confusing. I'm going to rewrite my ester here because my six-membered ring isn't looking very six-membered. So imagine a lactone, and I'll just deliberately give you this lactone. I'd like you on your own to think about what happens if we treat this lactone with sodium hydroxide and water. You should be able to think about this on your own. We've also talked about ammonolysis reactions. And so imagine this lactone with, let's say, methylamine. And again, think about these on your own. You should be able to think your way through the chemistry that's occurring at this point. All right, what else do I want to say at this point? As I said before, amides, for that matter, nitriles, are generally less reactive toward nucleophiles than esters. That nitrogen is less electronegative. That nitrogen of the amide group is less electronegative than the OR group, than the oxygen of an ester group. So in general, amides, and as I said, for that matter, nitriles, react more sluggishly. In other words, if I just mix an ester with sodium hydroxide in water and the ester dissolves, it'll generally react relatively quickly. It'll hydrolyze relatively quickly. If I take an acetamide like sodium hydroxide and put it in water, generally I have to warm this reaction up. Delta means heat, or let it go for a long time in order for the hydrolysis reaction to occur. And as I said, this would be the same. We talked more about nitriles before, but this would be the same for a nitrile. In general, you could go ahead and eventually hydrolyze your nitrile down to a carboxylate, stopping at the acetamide. In all of these, again, you should be able to think your way through the mechanism, but the basic gist of the mechanism in all of these reactions is the hydroxide anion is a nucleophile. It's going to attack the carbonyl group, and you should be able to think your way through these types of mechanisms. Thoughts or questions at this point? All right. I think where I want to end today's discussion is in some very practical chemistry in the synthesis of amides from carboxylic acids from amines, and if we have time, maybe the synthesis of esters as well. So as I said before, if you were to just mix a carboxylic acid and an amine. I'll just write these sort of generically as RCOOH and R prime 2 NH2, but it could be methylamine, primary amine. It could be dimethylamine, a secondary amine, could even be ammonia. If you just mix them together, you're going to get an acid-base reaction. But in the presence of the reagent DCC, I'll show you what that is and how this occurs in just a moment, you get an amide. DCC is often referred to as a coupling reagent. DCC stands for dicyclohexyl carbodiamide. Its structure is the carbodiamide group with two cyclohexane rings, two saturated rings, not benzene rings, but saturated rings attached to it. This molecule is a member of the carbon dioxide family of all things. Remember, I've been making this analogy between nitrogen and oxygen and saying many of the reactions aren't that different. The carbon's in the +4 oxidation state. You have two double bonds to nitrogens in DCC. In CO2, you have two double bonds to oxygen. Anyway, this reagent historically has been extremely useful for forming amide bonds. It's a very simple reaction to carry out operationally. And I know before, when I alluded to DCC, I talked about how horrible an allergen sensitizer it is. We used to use this reagent in my laboratory, but part of the principles of trying to work safely is whenever possible, choose safer reagents. So for you and your textbook, I think DCC is a perfect choice. For the researchers, graduate and undergraduate in my laboratory, they use this molecule, which has two isopropyl groups and is called DIC, diisopropyl carbodiamide, which is still prone to creating allergies, but much less so. Anyway, you can use DCC in your chemistry here. So let's take the abstract and reduce it to the concrete. If you take a carboxylic acid like benzoic acid, and you take an amine like ethylamine, and you mix them in the presence of DCC, you get the amide bond formation. So the product of this reaction is N-ethylbenzamide. And the mechanism of the reaction, I'm not going to go into excruciating detail, but the DCC reacts with the carboxylic acid to form an intermediate. The carboxylic acid adds to the DCC. I'm just going to abbreviate those cyclohexyl groups as CY. The carboxylic acid forms an intermediate that looks a heck of a lot like an acid anhydride. You notice the analogy here. Oxygen and nitrogen are very similar. Acid anhydrides basically are an activated carboxyl group, and you've got the same thing over here. Remember, I've made the analogy between nitrogen and oxygen. And so this molecule, this intermediate that forms is electrophilic. And you can think of the nitrogen as attacking the carboxyl group that's been activated and pushing electrons up onto the oxygen to generate a tetrahedral intermediate. So as I said, this intermediate here is very much like an anhydride. Thoughts or questions? So the byproduct of reaction is dicyclohexyl urea. And again, I'll just write this I'll write it out here just so we don't get too abstract for you. I'll write the cyclohexyl groups here. So sometimes this gets called DCU, dicyclohexyl urea. Anyway, that's the gist of the chemistry. Your textbook writes the activation of the carboxyl group as first protonating the nitrogen of DCC and then the carboxylate adding to the protonated DCC. I think honestly, a better way to think about it is both of those steps, and then the carboxylate adding to the protonated DCC. As I said, I think the way to think about it is both of those steps occurring at once in a reaction that looks kind of like a Diels-Alder reaction. It's called an Ene reaction, but I wouldn't worry about that in too much detail because I think the general principle is you add the carboxylic acid to the DCC, you form this anhydride-like intermediate that then a nucleophile can attack. You can use a similar variant of this reaction for the synthesis of esters, where you take a carboxylic acid plus an alcohol, and you carry out the reaction with DCC, and you usually have to add another catalyst called DMAP to make this reaction go. The alcohol is less nucleophilic than the amine, one of the principles that I've been talking about. So DMAP is 4-dimethylaminopyridine. And DMAP goes ahead and intercepts the intermediate. So here's our intermediate that forms with the DCC. And that intermediate isn't quite reactive enough to react to add the alcohol group. The alcohol reacts really slowly with this intermediate. What the DMAP does is it intercepts the intermediate, and I'm not writing a detailed mechanism here. It intercepts the intermediate, and that intermediate that forms is electrophilic enough for the alcohol to then add. So because the DMAP is ultimately released, but it helps by being a nucleophile, the DMAP is referred to as a nucleophilic catalyst. Anyway, this is a very useful reaction to make esters. And even though it's not in your textbook, I think it's worth adding to your arsenal of chemistry. I just put in the P on DMAP that I had dropped. It's worth adding to your arsenal of chemistry because I think it will make your life easier in thinking about chemistry. All right, another very good way to interconvert to make esters is to make the carboxylic acid into the acid chloride. If you take a carboxylic acid and you first treat it with SOCl2 with thionyl chloride, you'll get the acid chloride. In a separate step, you can add the alcohol, often, as I said, with some base. I had mentioned this when we were back in the previous chapter. I said often you'll use triethylamine or pyridine. As a base, and also to avoid acid inhibiting the reaction, at least in the case of amide formation, which I'll show you in a second. So basically the same type of thing you can do to make amides. You treat with, that's SOCl2, I'll write it again, thionyl chloride, and then an amine, and I can just write that as R prime NH2. You could do that with a primary amine. You could do it with a secondary amine. You could do it with ammonia. But often in these reactions, you add these triethylamine or pyridine as a base. And in all of these cases, what's happening is in the first step, your carboxylic acid is reacting with thionyl chloride. Thionyl chloride actually has a lone pair on sulfur. Your carboxylic acid is reacting with thionyl chloride to give rise to the acid chloride. The byproducts of this reaction are HCl plus sulfur dioxide. And if you want to think about the mechanism, and I really love this because it sort of shows common themes in organic chemistry. If you want to think about the mechanism, albeit maybe not at a super high level of detail, really is the first step, the first couple of steps involve the attack of the carboxylic acid on thionyl chloride. To form, again, an intermediate, and I'll just write plus HCl as a byproduct, but again, to form an intermediate that looks a heck of a lot like an anhydride if you sort of have a little bit of fluidity of mind here. In other words, the thionyl chloride is activating the carboxylic acid by forming an electrophilic intermediate. And then in the next set of steps of the reaction, chloride adds, and again, I'm not going into fantastic detail, and that's deliberate because I think people get a little bit sort of stressed out. I'm gonna actually write things a little bit more neatly here. People get a little bit stressed out sort of about all of the details here. But at that point, your chloride, Cl minus, can add to your activated carboxylic acid, and tetrahedral intermediate breaks down, and that kicks out sulfur dioxide and chloride. That gives rise to the acid chloride plus sulfur dioxide, which, as I said, has a lone pair on it, plus chloride anion. And so this conversion of a carboxylic acid to an acid chloride then also opens up the gateway to you for generating amides, to generating esters, and even to generating anhydrides by reaction with a second molecule of carboxylic acid. So on that note, I think I'd like to wrap up our discussion of chapter 20. The homework problems are going to give you a very good feeling for the types of chemistry that's involved and how these reactions work, mechanisms, synthesis, and other courses of reaction. I will look forward to seeing you on Thursday, and we'll just start the discussion of chapter 21. Have a good rest of your day. Bye now.